Let's explore segment trees and Fenwick trees. These are data structures that help us efficiently perform range queries and updates on arrays. Consider some common range query problems. The first one is the range sum query, where we need to find the sum of elements within a given range, say from index I to index j in an array. Next, we have range minimum or maximum query, which involves finding the minimum or maximum value within a specified range in an array. Then there's the range update query, where we update all elements within a given range, for example, adding a certain value to all elements between index I and index j. Finally, we might encounter range XOR, GCD, or LCM queries, involving operations like XOR, greatest common divisor, or least common multiple over a range. Now let's look at a naive approach to solve the range sum query problem. In this approach, we iterate through the array from index I to j and compute the sum. This is demonstrated by the code snippet provided. The time complexity of this naive approach is order of n per query, where n is the number of elements in the array. A segment tree is a powerful binary tree data structure designed for efficiently storing information about intervals, also known as segments. It is particularly useful when dealing with range queries and updates on arrays. Each node in the tree represents a range of the array and allows for performing operations like finding the sum, minimum, or maximum within a specified segment in logarithmic time. Here are some key properties of segment trees. The first one is the binary tree structure. Each node has at most 2 children. Each node represents a range of the array, storing information relevant to that range. The leaf nodes represent individual array elements. Parent nodes aggregate information from their children, storing combined results. Segment trees enable order of log n time complexity for both query and update operations, making them highly efficient for dynamic range problems. Now let's discuss the construction process of a segment tree. The first step is to create an array called tree, of size 4 times n, where n is the size of the input array. The second step is to start with the entire array range, from index 0 to n-1. Recursively divide the range into half. Build the tree bottom up, starting with the leaf nodes first, and then combining them to construct the upper levels. For each node, store the result of the operation, such as sum, minimum, or maximum, for its corresponding range. Here's some example code. The time complexity for building a segment tree is order of n, and the space complexity is order of 4n, which simplifies to order of n. Let's explore how to use a segment tree to perform a range query, specifically finding the sum of elements from index L to index R. To query the sum of elements from index L to index R, we recursively navigate the segment tree and combine results from relevant nodes. There are 3 cases to consider. First, complete overlap. If the node range is completely inside the query range, we simply return the value stored in the node. Second, no overlap. If the node range is completely outside the query range, we return 0, indicating no contribution to the sum. Third, partial overlap. If the node range partially overlaps the query range, we split the range into 2 halves and recursively query both children, combining their results. The time complexity of the query operation is order of log n per query. Now let's understand the update operation in a segment tree. When updating a single element, we need to update its corresponding leaf node and all of its ancestors in the tree to maintain the correct sum values. Here are the steps involved. First, locate the leaf node that corresponds to the index you want to update. Second, update the value of the leaf node to the new value. Third, recursively update all parent nodes from the leaf node up to the root. For each parent node, update its value by combining the values of its children. This ensures that the segment tree reflects the updated array. The time complexity of the update operation is order of log n per update. Let's dive into the code implementation of a segment tree. We start by defining a class called segment tree. In the init method, we initialize the segment tree with the input array. We store the length of the array as n, the array itself as array, and create a tree array of size 4 times n. We then call the build method to construct the segment tree. The build method recursively constructs the segment tree. If the start and end indices are equal, it means we've reached a leaf node, so we store the value of the array at that index in the tree. Otherwise, we calculate the middle index, recursively build the left and right subtrees, and store the sum of the left and right subtrees in the current node. The class encapsulates the tree array, source array, and operations in a clean object-oriented way. The tree size of 4 times n ensures we have enough space for all nodes in any valid segment tree. It is a simple recursive implementation with clear node indexing for left and right children. Let's consider an example to illustrate the usage of a segment tree. Given an array 2, 5, 8, 1, 9, 3, 7 for we want to perform range sum queries and updates efficiently. First, we query the sum in the range 2 to 5. Then we update the value at index 3 to 10. Finally, we query the sum in the range 2 to 5 again. So the first query returns 21, which is the sum of 8 plus 1 plus 9 plus 3. After updating the value at index 3 to 10, the second query returns 30, which is the sum of 8 plus 10 plus 9 plus 3. Here's the code demonstrating how to use the segment tree. We first create a segment tree with the given array. Then we perform the query and update operations as described above. Now let's explore Fenwick trees, also known as binary index trees or BIT. A Fenwick tree is a data structure that efficiently supports cumulative frequency operations, including point updates and range sum queries. It allows us to quickly calculate prefix sums and update individual elements in an array. Here are some key features of Fenwick trees. They are more memory efficient than segment trees. They have a simpler implementation for certain operations. They offer order of log n time complexity for updates and queries. They are particularly efficient for calculating prefix sums. They take advantage of the binary representation of indices. Now let's delve into the two primary operations supported by Fenwick trees. Query, which retrieves the prefix sum, and update, which modifies the array. First query, prefix sum. To compute the sum of elements from 1 to index, we traverse up the tree using the bit manipulation property. This involves repeatedly removing the least significant bit from the index until we reach 0, summing the values along the way. The time complexity of this operation is order of log n. Second, update, point update. To update a value at a given index, we need to update all ancestors in the tree by traversing up using bit manipulation. This involves repeatedly adding the least significant bit to the index until we exceed the array size, updating the values along the way. The time complexity of this operation is also order of log n. Now let's examine the implementation of a Fenwick tree. We define a class called Fenwick tree. In the init method, we initialize the Fenwick tree with the input array. We store the length of the array as n and create a bit array of size n plus 1, since Fenwick trees are 1-indexed. We then build the bit array by iterating through the input array and calling the update method for each element. The update method adds a value to the specified index and updates all ancestors in the tree. The prefix sum method calculates the sum of elements from 1 to the specified index by traversing up the tree, summing the values along the way. The range sum method calculates the sum of elements between two indices by subtracting the prefix sum of the left index minus 1 from the prefix sum of the right index. Fenwick tree has fewer lines of code and simpler logic than segment tree. It uses exactly n plus 1 space compared to 4n for segment trees. It leverages binary properties of indices for efficient traversal. Let's compare segment trees and Fenwick trees to understand their strengths and weaknesses. Regarding functionality, segment trees support range queries and updates for various operations, such as sum, minimum, maximum, and GCD. Fenwick trees primarily support prefix sums and point updates. In terms of memory usage, segment trees require 4 times n space, while Fenwick trees require n plus 1 space. Both segment trees and Fenwick trees offer order of log n complexity for both query and update operations. Segment trees are more versatile, supporting a wide range of operations, while Fenwick trees are less versatile, focusing on cumulative operations. Segment trees are more complex to implement compared to Fenwick trees. When to use segment tree? If you need range minimum or maximum queries. If you need more complex range operations such as GCD or XOR. If you need range updates with lazy propagation. If flexibility is more important than memory usage, choose segment tree. When to use Fenwick tree? If you need efficient range sum queries. If memory constraints are important. If a simpler implementation is preferred. If you're working with cumulative frequency problems, then you can choose Fenwick tree. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.